Okay, I'm going to start. So I'm going to talk about graphical models this week. I'm going to kind of do a high-level overview of the stuff we talked about in class, add a few new things, and give a bunch of examples of machine learning problems where you would actually use graphical models, which we haven't talked about much in class yet. So as a recap, graphical models in general are just a way to write down any probability distribution. And the advantage of doing that is that if you have a distribution with a lot of variables, the graph lets you add in, the graph lets you account for a lot of the independences that basically reduce the dimensionality of the distribution that you need to represent a lot. So the advantage of doing the other advantage of using these kinds of representations, in addition to kind of being able to write down distributions, is that because you can write down those distributions, you can do machine learning methods with a lot of variables without assuming that the relationships are just linear or they're joint normal or something. You can build up much more complicated relationships between them and still be able to effectively deal with it. Another advantage is that, say you're doing like a car, you want to build an automatic car that could drive around on its own. An autonomous car is the word I meant to say. So that involves a lot of subsystems. One subsystem is, say, a vision tracking system where it looks at objects moving around, and another subsystem is kind of decision-making stuff. And you probably Google's autonomous car doesn't do this, but you could theoretically plug everything into one giant graphical model and just copy-paste in your model for vision tracking and your model for following the rules of the road and stuff like that. So you can deal with sub-problems effectively in a way that if you were trying to solve some classification problem with an SVM, you wouldn't be able to do because you have to combine the subparts. Another advantage is that if you have some prior information about your domain, if you know, so in the car example, you know a lot of things about how people move around, you know a lot of things about what traffic tends to do, what pedestrians tend to do. And you can add that to your model pretty straightforwardly and declaratively, where with other kinds of models, it's a lot harder and a lot less obvious to know how you're just going to add that to the system. Yeah, okay. Okay, so to recap, there are kind of, typically we talk about two broad categories of graphical models. There's undirected and directed. So I'm going to start with undirected for right now. So this is kind of the simplest possible graphical model. It's just one node, one variable, and no connections to anything. So with an undirected graphical model, what we're saying then is that the probability of our data is just some function of x1. Nothing fancy. It could be anything, basically. Now, if we add another node to the model, and we don't have them connected, then we're saying that it's basically some factor potential on x1 and another factor potential on x2, and they're unrelated. In this model, the two x1 and x2 are independent, and they're just modeled separately. And that's the normal factorization of independent things and probabilities. They just multiply. If we add a connection, then we're back to the, oh, it could be anything. We could have any connection between those two nodes, those two variables. Now, if we add a third one connected like that, then we know that x1 and x3, we're saying are only, their connection is kind of mediated by x2. The only possible connection between them is through x2. So in that case, we can write the factors as x1, x2, and x2, x3. And so x1 and x3 are conditionally independent given x2. That's just a separation thing for Markov networks. We could also add an arc there that then makes everything dependent again. But in a particular, yeah, so our factor then is just of anything. Why? Oh, okay. Yeah. Animation's just in dumb order. We can also do things like we can add a connected set of variables that are only connected to each one of these. So in this case, we have a bunch of x's that are connected in a sequence, and we have some y's that are connected only to the respective x. So this kind of model comes up a lot where you have some kind of sequence, usually something happening over time, like language or some kind of events, weather, or something like that. And then the x's are a model of the latent state, and then the y's are some random function of that latent state. So it could be, for example, if with a language example, you could have the x's being part of speech of the words. And so if you know the last part of speech, then you have a different distribution on the next part of speech. And then if you know the part of speech, you have a distribution on what actual word it is. So that kind of model, it's not a great model for parts of speech, but for a lot of things, it's pretty useful to be able to model sequences like that. And it's pretty closely related to a model some of you probably know called the hidden Markov model. Okay, we also have directed graphical models where the connections are directed. So a lot of times we can interpret that as kind of vague, some kind of vague causality argument, in that if we know that A causes B, we usually want to draw an arrow from A to B. But if you actually write out the factorizations, of course, they're equivalent. So in this case, we have, it factorizes as x1, x2. We have, or x3, there's three of them. So the way this factorizes the distribution is like this, in this case. So the general rule is the probability of something given its parents. So in this case, x1 is no parents, so it has its own probability. x2 is given x1 only, and x3 is given x2 only. And that makes sense to everyone? Everyone's good with that? Cool. So you said A causes B. What did you say? B and also A causes C? Yeah. Like that? Yeah. So that's what it would look like. So it's just the things given their parents, right? So it's P of A, and then B is P of B given A, and C is P of C given AB. Make sense? And so that's equal to P of ABC, because, so there's a general rule of probability that you can write things as P of A, P of B given A, P of C given AB. Oh, in this case, we actually have a full. That's the exact same factorization. So you can always write probability distributions like that. That's just the chain rule. But so in this case, where we have A, B, C in the chain like that, in that case, then the probability of C given A and B is equal to the probability of just C given B, because C is conditionally independent of A given B in this case. Yes, sorry. Okay. All right, and we can also do a directed version of that output thing. This is actually the hidden Markov model. So the probabilities terms here then would be P of x1, P of x2 given x1, P of x3 given x2. That's the normal chain. And then we also have P of y1 given x1, y2 given x2, y3 given x3. So that's the likelihood function for this thing called a hidden Markov model. And you can do that for any graph that you want to draw. The requirement for the directed versions is that it be a directed acyclic graph, a DAG. So there, you can't have any cycles, because then your probability terms up would end up being like P of B given B, and that makes no sense. You can't do that probabilistically. So we require that it be acyclic. But that's okay. You can represent, so for any probability distribution, you can write down a Bayes-net or a Markov random field, an undirected graphical model or a directed one that represents that distribution. The only, you just might not be able to write down a graph structure that represents all the independences that are present in the distribution. So for a particular distribution, you can write it in any form you want, but which form is best kind of depends on what kind of independent structures there are, and also whether whether having a directed graph is natural in that case or not, which sometimes it is, sometimes it's not. Okay, so we're going to go into some specific examples of representations now. So the first one is a pretty famous NLP type thing called latent Dirichlet allocation, or LDA. It's the simplest and first instance of what's called a topic model. So in this case, we have, okay, so first of all, this plate notation, these boxes, what that means is, all right. So the inner part of this model, so we have Z, W, W, and those, beta, I'll just try it all, theta, alpha. Okay, so what this notation means, when we draw this this end thing, what that means is we actually have Z1 pointing to W1, Z2 pointing to W2, and so on up to N. And then this outside term, this theta, points to each of those Z's. So the plate, the box there with the N just means replicated N times. Okay, and then the outer box means M times, so we have N times M of these W's in here. So what this model is for is basically if you have a bunch of text documents, according to this model, the way text documents work is they have a bunch of words in them. Each word is about some topic, and each document is about a set of the topics. So you might have one news article that's about politics, and whatever, it might be about like, you know, politics and New York, and then you would have some words that are about politics and some words that are about New York, and then lots of other general purpose topics for various other things. And you might have another article that's a news article about, well, it's a fluff piece about pets. So it has a, you know, it has a topic about dogs and a topic about cats. And so when you do that in this model, the way the model works is you have a bunch of words in the article. Each word, it comes from a particular topic. So this Z is a variable that assigns a word to a given topic. The theta is the distribution of topics for that particular for that particular document. And then this alpha is a prior over topic distributions. So according to the model, the way that you go and write a news article is first you choose what topics it's going to be about. So you take this prior, which is a Dirichlet distribution, and choose a bunch of topics, and then and then you have the number of words in the document. For each word, you choose which topic it's from according to another distribution, like a multinomial distribution on those topics. And then once you have the topic for each word, you choose the word from that topic according to another multinomial distribution. And then this beta here that I haven't mentioned yet is it's another prior on the words for each topic. So the details don't really matter. That's not what we care about right now. But the basic idea is that you can set up a graphical model where the only observed values are the words in your document, and then you add these latent variables for things like topics that aren't actually observable. They're not particularly well defined, but you can get an estimate of what the topics might be by defining this model. And so once you've set up this model, you can ask questions of it, you can learn it using more or less general purpose graphical models tools. And then once you've set it up as a graphical model, it's really easy, or pretty easy, to modify the model to add new things. So you can do something really complicated, like this model is from a paper a couple of years ago where what they did was they took a big corpus of tweets that had geolocations on them. So they took the things that a person said, the words, and then modeled them as being based on both the topics that they're talking about and also what region they're in. And so they were able to pick up some region-specific linguistic variation just based on a big corpus of tweets. And to do that, they just add a whole bunch of parameters to this model, a whole bunch of variables to this model, and do more or less the same thing you would do for basic LDA, and pick out this cool linguistic model of English language usage. Another way you can extend them, the details don't really matter here, but this is basically another way to extend LDA to operate on, instead of vector words, operate on sets of words, basically. And so you can use that for things like detecting anomalous groups of points rather than anomalous single points. And because it's a generative model, you assume that your sets of points that you have, which might be, for example, if you have a big astronomical survey, and you have galaxy clusters, you want to find weird galaxy clusters that astronomers might be interested in. You can do something like, so you can find galaxy clusters that contain weird galaxies. That's the kind of thing that we talked about with novelty detection in SVMs. And you can run that and find galaxies that look weird. But sometimes there are galaxy clusters where each individual galaxy is pretty normal, but the combination is weird. Like some of them are really old and some are really young or something like that. I don't actually know anything about astronomy. And so by just basically adding another plate to this model and tweaking the algorithms a little bit, you can come up with a way to get group anomaly detection. Yeah. This one?
I'm trying to understand what the K plate, like the beta, the beta and
yeah.
so that you said that means repeated K times, right?
Right. So the observed thing, these are the elements of the group. Oh, you're talking about this K and N? You're talking about the arrow between beta and X here, or what?
The one before that. Like
Okay.
this one, yeah. So here I can understand that theta is generating like n of those z's, but here it itself is coming k times and the beta itself is coming k times. So
Right. So this this is a little weird. This notation isn't absolutely standardized. So I think what this means is that there are k etas from 1 to k, and there are m times k betas. So there's beta 1, 1, which for each value of k, the beta only gets input from the corresponding kth value of eta, but there are m of them. So I think that's what's going on here.
So, and then the next arrow would be like 1 beta generates n of xmn.
So here it's each of the xmn's gets inputs from all of the k betas. All of the k betas for that particular m. Yeah. I mean, the details of the notation are kind of weird. It's just, that's not that important. I think normally these would be written, like these two plates would be written overlapping rather than separate like that. Okay, so another thing you can do with graphical models is you can do, you can come up with hierarchical models where you have basically latent factors that influence each other. So in this case, what they were doing, this was some political scientists / statisticians. So what they did was they took this survey across the US that had, it wasn't an enormous sample size. So they had, some results from each state and in each of a bunch of ethnic / religious groups, but they didn't, each of those combinations of state and ethnic religious group is fairly sparse. So the estimates are somewhat noisy. So you can see that in each of these categories, the states look pretty non-smooth in a way that's probably not true. There's no real reason to think that Colorado would be so dramatically different from Nebraska in this particular age category, or racial, ethnic category, and income bracket. I think those are income brackets, right? Yeah, so columns are income brackets. So what you can do is you can basically add some smoothing across, say, the model that you build basically assumes some smoothness across the different, saying, everything should be fairly smooth for the same income level, should be fairly smooth for the same ethnic, religious category, should be fairly smooth for the same state. And when you add all that smoothing together, you can get out these, visualizations of how the combinations affect each other in a way that seems much less noisy and is much easier to interpret what's going on. But it's finer grained than if you just took the average. You can still see spatial variation. You can still see income variation. It's just, it's smoother and probably closer to what the true values look like. Okay, so those were all kind of vaguely similar topic model type things. Here's a completely different setting that you can still phrase as a graphical model. So imagine you have a big matrix. The entries are Rij. And you think that the matrix is low rank. So one reason that might be true, so first of all, if it's low rank, that means you can write it as the product of a tall matrix, or a skinny matrix and a fat matrix, right? So that means that each entry Rij is the inner product of some entry of some row Ui and some column Vj. So where might you care about this? Well, so where this model was developed was in trying to win the Netflix prize, which is where, so basically Netflix, at least as of about 5 years ago, really cared about getting really good ratings based on pretty sparse information about what users like what movies. They want to be able to predict what movies a given user will like. So you can model that as each row in this is a user, Each column in this giant matrix is a movie. So it's a big matrix, and you only observe very, very few of the entries. And you want to be able to predict the rest of the entries based on that. So one not terrible model is that there are a set of latent factors where whether you like a movie is kind of a combination of whether you like action movies and whether it's an action movie, whether you like romantic subplots and it has a romantic subplot or doesn't, etc. You can model it as a linear combination of those things and get out a reasonable estimate of the matrix. So in order to do that, what these guys did was they wrote it. So to find this low rank approximation, one way to do it would be to say, well, Rij is ui.vj plus noise, or you could also write it as normal distribution around that product, and then you add a prior on u and v, and then you have this graphical model where each Rij is a combination of the vj's and the ui's, each of which, in turn, their distributions depend on some hyperparameters. So you can do a pretty good matrix factorization as a graphical model. And if you want, you can extend it to make the priors on u and v more complicated and kind of better. The details don't really matter here. Basically, in this model, what they were doing was they just assumed a fixed u and v. Here, they're integrating over lots of possible values of u and v. And then the weighting for those values depends on the hyperprior. So that makes it a little less sensitive, or actually a lot less sensitive to the particular parameter values that you choose and stuff, and lets you get a much better result out. Okay, so every example so far has been of directed graphical models. Here's one of the more important examples of an undirected graphical model where people really use it a lot and it's a big deal. So imagine you have an image and you want to split the image into component parts. So the model that people typically use is something like a grid model of a Markov random field where you have kind of a latent state along a grid. So the latent state says, is this part of a cow? Is this part of grass? Is this part of a car? Whatever. And those depend on each other under this assumption, they only depend on their neighbors. And then the actual pixel value that you see is a random function of whether it's a car or not. So if it's part of a car, in this case, it'll probably be silver, but it might be a various grade of silver. It might be red for the light or bluish for the window, that kind of thing. So doing that, the typical way that people do this then is first off, instead of working at a pixel level, you could work at a pixel level, but that's a lot of computation and doesn't really help that much. So people break them up into superpixels, which are these contiguous chunks of an image that are pretty visually similar, fairly small, pretty close together. So when you have these superpixels, the way that you would do image segmentation based on this course up to graphical models would probably be something like, for each little superpixel, look at that patch and build a classifier that says, does this patch look like part of a cow or part of a car or part of grass or whatever? And if you do that, you get segmentation results that kind of look like this, in that, so like the road is mostly together, the building in the background is mostly together, but there's a lot of noisy bits. It's not very coherent, and the cow is kind of terrible. The cow does really poorly because the white parts of the cow and the brown parts of the cow don't really seem that similar to the classifier training algorithm. This part looks pretty different from that part. It's no good. But if you build this kind of Markov random field on the superpixels and basically add in information that adjacent superpixels are more likely to be from the same class, then you get really good segmentations without doing too much else. Really like much smoother segmentations where there's a lot less noise and crap going on. Okay, so that was a bunch of examples of applications of graphical models in machine learning type areas. Are there any questions about the stuff I just talked about? Okay, so we've pretty much just talked about here's a representation, here's some things you can do with it. Well, how do you actually do those things? So we talked a fair amount in class so far about inference in Bayes nets, where you basically, you want to answer some probabilistic question based on the model. You either want to say, here I have this sequence, how likely is this sequence under the model? Or you might want to say, what is the conditional distribution of this variable given this other information that I've seen? So for example here, what is the segment of this, basically what are all the values of the x's given all the observed pixel values of the y's, that kind of thing. So we talked in class about how to do that with Bayes nets, or with actually undirected fields also, using message passing, which was basically you do variable elimination after you've built the junction tree, so you have a tree, and so on. So that was, so that's an algorithm that makes it, reduces it from exponential in the number of variables to exponential in the tree width, which if the tree width is small, that's great. If the tree width is big, that's not so great. It's still exponential. So in a grid like this, the tree width is exponential still. And in a lot of models like that, it's still, message passing is not, it's still exponential. It's still too slow. Also, we've only really talked in class so far about binary variables, but a lot of the time you care about continuous things. You have continuous measurements, you have continuous brightness, pixel values, whatever. Most of the things we deal with are probably continuous rather than binary or small value, small number of categories. So in that case, message passing would require doing these integrals that we usually, almost always, can't do in closed form. So we can't do message passing there either. So we have to turn to these approximate methods. There's three big ones. In the case where you have a grid or something, and where you don't have to worry about continuous distributions, but you can't build the junction tree because it's too big, you can do something called loopy belief propagation. In general, you can do variational approximations, you can do sampling, which I'll talk about more in a second. I also skipped another way that we haven't talked about in class to do exact inference that's, in special cases, much faster than message passing, is for certain kinds of graphs, you can do inference based on solving max flow or min cut problems. And because we know how to do those fast, we can do inference pretty quickly on special kinds of graphs with that. Okay, so what is loopy belief propagation? We've covered belief propagation in class, but we said it only works on basically trees. So what loopy belief propagation is you just ignore the fact that it only works on trees and you just do it, and you iterate. And a lot of the time, that'll get you it'll converge to the right answer fairly quickly in many situations. But people don't really understand yet exactly what those situations are. There are some where we know work, but there are lots where we don't have any necessary conditions, and we have some sufficient conditions, I think, is the current state of it. So the reason that people started trying this basically was this thing called turbo codes, which are error correcting codes that are used in cell phone networks, things like that. And people figured out that turbo codes were actually an instance of loopy belief propagation. And they said, hey, this works really well, so loopy belief propagation must be something worthwhile. Okay, so something that does work more generally is called variational approximations. So the basic idea for variational approximations is we have this model, this graphical model, where inference is hard. So what we want to do inference is choose some choose some model that's as similar as possible to the graphical model where inference is easy, and find the most similar such model. So what we do is we choose some family of distributions that we know how to do inference on. So a lot of times that'll be like a multivariate normal distribution, or it could be something where we assume that all of the variables are independent, and then we can figure out the best, we can figure out how to do inference in that case, assuming all the variables are independent in a lot of situations. Basically, if all your distributions are conjugate and exponential family, then you can do fully factorized distributions pretty easily. And so that's obviously, it's not the full distribution, and the answers you get will not be the same as what the actual distribution will give you, but a lot of times they'll be pretty close. And they'll be good enough to use for other purposes, even if they're not super accurate results. So the way you do that is you choose that family. You choose a family, hopefully that's the richest possible family you can deal with, and then you find the closest member of that family to the actual graphical model by minimizing the KL divergence of Q from P. So KL divergence, you know from recitation last week and from class, is kind of a measure of distance on probability distributions. So if it turns out that the true distribution is in our approximating family, we can get that to 0. Almost always that's not the case, but lower is better. And the reason, or one of the reasons that we do Q from P instead of P from Q, like instead of the other order in the KL, is that we can usually compute this. The other order is harder much of the time. So the reason for that is that KL Q from P is the integral of is that, right? Which is the negative entropy of Q minus the integral of Q of X log P of X. So typically we choose a family where we can get the entropy easily, and also where we can take expectations under it of the log likelihood easily. Doing it in the other direction would require knowing the entropy of the graphical model, which is hard. That's a hard problem, harder maybe than the problem we're trying to solve, so it doesn't help to do it that way. But in a special case, you might be able to do it the other way too. Okay, the last big way that you can do inference or approximate inference with graphical models is, instead of directly answering the probability question, what you do is you take a bunch of samples from the model, you take a bunch of samples from almost the model, take approximate samples from the model, and then you can answer whatever probabilistic question you want to ask based on those samples, just from the frequency that it happens in those samples. So if you wanted to ask a question like, you know, the mean of x1 given x2 is some value, x3 is some value, then what you would do is you would fix x2 and x3 to those values in your graphical model, sample from the model, and you get a bunch of x1 values, you take the mean of those. That's how you answer that kind of question. And for any other probabilistic inference question you might want to ask, you can do it from samples, usually without too much trouble, if you can get the samples. So there's a couple different ways to get the samples. In low dimensions, the easiest thing to do is called importance sampling, which is, let's say we have some hidden latent variables z and observed variables x. So these are the variables that we know the values of. Those are the variables we don't know the values of. So what we can do then is, to sample this way, we can just take samples from the prior on z unconditionally, and then we can weight those samples by the likelihood of z given the samples that we have actually seen. Okay, that method doesn't always work that well, especially in high distributions, because most of the samples that you take will be weighted very low, just in that the probability mass is not, the likelihood matters more than the prior, right, usually. So if you're sampling from the prior, you'll be in some weird part of the space that's very unlikely, and your samples will mostly be wasted. So you can do Markov chain Monte Carlo, which, so the basic idea of MCMC is you start from some model in your graphical model. So you assign all the parameters to something. Then from that point, you say, okay, I'm going to propose a new point as a next sample from this distribution. And you can do that. There's so many papers written on possible ways to do that. The easiest way is you just do a normal distribution around your current point. And then based on the likelihood ratio of the current point and the proposed point, you'll either move to the new point or you'll say, no, the new point's no good, I'm going to stay where I am. And if you do that in the limit, eventually you have a set of samples from the original distribution. There's also a special case of that called Gibbs sampling, which the way that you propose a new point is you take, so if you have some graphical model, whatever. So you have your model, and you have current values for all of these parameters. You have a particular value for A, B, C, D, E, F. So what Gibbs sampling does is it says, okay, I'm going to look at D, and I'm going to change D and leave everything else the same. And the way that I change D is I look at the distribution of D when all the other variables are observed. And so in a Bayes net, typically that's pretty easy because that's exactly what the model is. It's the distribution of D given B and C, and A, E, and F, but in that case they're independent. So you have that, what your model is all of those probability distributions, and if you've chosen your distributions to be conjugate, then you can sample from D given B and C easily. And so if you have a conjugate model, you can do Gibbs sampling pretty efficiently. So what you do is you start with some arbitrary value or zeros or whatever, and then you update one value, you update the next value, update the next, go on, continue. You can update more than one value at once. You can sometimes integrate out some of the values. There's lots of variations you can do. So basically there's a whole class on graphical models, and it spends a couple lectures on MCMC. There's books on it. Yeah. But so that's the basic idea. Gibbs sampling is the most common MCMC method in graphical models because typically people choose their models in a way to make Gibbs sampling easy. Okay. So we just talked about when you have a model, what do you do? What do you do with it? So is everyone more or less happy with how to do inference? Like not necessarily the details of all the algorithms, but you have a general sense of how inference works? Okay. So how do you get the model? Well, so first of all, let's assume that you've decided on the structure. You know how your variables are all going to be connected, and you've decided on what family of probability distributions will be for each one. So if they're all binary values, then you could just deal with tables, which is mostly what we talked about in class. So the distribution for D would then be just these 4 numbers here would define the distribution for D. So you have four independent probabilities for D, depending on the values of its parents. So that's one option for binary variables. If you're doing continuous variables, then typically you'd assume Gaussian or chi-squared or whatever, some standard distribution. Not necessarily, though. You can also do anything that gives you a probability distribution. You can do some kind of crazy deep learning generative model, like a neural network type thing. You can do another BaseNet if you want, for some reason. You can do whatever. So how do we get the parameters of those based on data? Well, if we've observed if all of our observations have all of the variables, then like we talked about in class, this is just the problem of fitting whatever probability model you've chosen. So in the binary case, you're just fitting these P1, 2, 3, 4s, which typically the maximum likelihood would just be count your samples. You might add smoothing to that. You might also add some regularization that P1 and P2 should be kind of similar. That you can add that kind of thing. It's as general as fitting a probability distribution ever is. So all you have to do, though, is fit a probability distribution at each node given its parents. Okay. In undirected models, unfortunately, you can't, it's a little more complicated. You can't just take the samples and look at the parents because everything kind of interacts with everything else all over the place. But it turns out that if you write down the likelihood function for the whole model, then you end up with a convex optimization problem that you can solve the same way you solve any convex optimization problem. So you can maximize the likelihood for a Markov random field through gradient descent or whatever variant on that you want to use. The problem, or the annoying thing there that makes it slow, is that at each step of the gradient descent, you need to do inference. So your inference needs to be really fast. And if your inference is approximate, the way that that interacts with the optimization causes all kinds of issues. There are all kinds of things you can do to make them mesh together more. But theoretically, all you need is inference as a subroutine. OK. Part of the point of graphical models, though, is that we don't have to observe every single variable. We can have hidden variables. So the way that we do hidden variables we touched on in class, and I'm going to kind of touch on again now, is we usually use this algorithm, or this class of algorithms called expectation maximization. So the idea here is if we've observed everything, then it's fairly easy to learn the model. We just talked about how to do that. But if we haven't observed everything, we pretty much have no idea. So what we do in EM is we pretend we've observed everything by taking the most likely value for all of the variables we haven't observed, pretending that's the actual value, training the model. And then once we've trained the model, we update the model, and then we get the most likely values for the hidden variables and repeat. So that, as an optimization problem, it's not convex, it's biconvex. So there are lots of possible local minima or maxima, depending on if you want to call it maximization. And so you have to, basically in practice, you have to start it a couple times and try different parameter values and see which one comes out best. But it works. And it's usually, obviously it can be slow for really big models, but in general, it's a fairly fast way to do this. And if you try random restarts and different parameter values, you typically get a pretty good optimum doing this way, depending on the model. You can come up with a model where you get out bad values most of the time. But most reasonable models, you get good values most of the time, hopefully. OK. So we have an idea now of, if you have a graphical model, structure, like you've decided on all the probability distributions and stuff, and we have some data, how can we learn the values of the probability distributions? How can we basically pick a probability distribution at each node? So the other problem is, how do we come up with that model in the first place? How do we choose the structure of the model? Well, usually, if you can, you want to do, you want to put as much of your knowledge about the problem into it as possible, because structural learning is really hard. If you have only 10 variables, there are a quintillion possible structures to search through, which is 10 to the 18. It's a lot. So you can't possibly try them all. And even just trying random ones is no good, because you'll never get to the good ones if you have a 1 in a quintillion shot of getting the best one. So basically, you have to start with a model and do local search, where you start off with a set of variables, and you say, okay, I'm going to try adding that edge. Does that help? Is that good? I'm going to try breaking that edge. Does that help? So on. And you do that. You do random restarts on that, and there are some other fancier things you can do that take bigger steps than that. But you can kind of cover the space not horribly by doing that. So there's also the question of, well, how do you decide how good a structure is? Normally, we would want to use likelihood, because maximizing likelihood is kind of our guiding principle for most things we do. But the problem is that if you're doing model selection, maximizing the likelihood is no good, because a more complex model will always have a higher likelihood. So you have to either penalize the search somehow by basically adding a penalty for more complicated models. And in a DAG, it's not necessarily obvious what a more complicated model is, but it could be something based on number of edges, that kind of thing. It could be like a tree width type thing. Those are some possibilities. You can also try to do something based on cross-validation type stuff, but that gets really expensive in that there are quintillion possible models you're searching over, and at each one you're doing cross-validation. So that can be hard to do in practice. But so it's not a hopeless problem to do structural learning, but it's hard. Okay, so we've talked about what a graphical model is, like what different possible representations are, when you have a graphical model, how do you answer questions with it, and also how do you come up with a model in the first place. So we've kind of done an overview of everything you do with graphical models, and that's all I have for today. So any questions about this stuff at all? If you're interested in it, there's a whole class next semester, and you cover a lot of stuff. Okay.